Hello again, welcome to another lesson in geometry. Today we are covering Chapter 1, Section 3, Measuring Segments. So remember last time we learned was a segment was a part of a line that has an endpoint on both ends, okay? So infinite number of points in between those two endpoints. All right, so our warm-up. Use the figure below for exercises 1 through 8. So here's my figure. Note that Rn pierces the plane at point N and is not coplanar with V. Okay, so it's not coplanar with plane V, and it goes through N there. So it's that's why this part is dotted looking here. Okay, because that's the bottom part underneath the plane. All right, name two segments shown in the figure. So any two segments, we feel like there are bazillions of them. So we could say segment Rn. Okay, that means that is ignoring the arrow part that go on forever. That's just the line segment that starts at R and ends at N. We could also say segment AN or NA. Okay. What is the intersection of lines CM and RN? So CM is here and RN is here, and they intersect at point N. So C, M, and N are collinear because they're on the same line. All right, name three collinear points. So we know C, M, and N are collinear, but A, N, and X are also collinear. So I'm going to name those. Okay. What are two other ways to name plane V? So plane V is the whole plane. We just need to pick 3 points on that plane. So we could call it plane ANC. Or any other 3 points that are on the plane, as long as those points are not collinear, A, N, M. And there are a few other ways. Okay, just pick 3 points that are on the plane that are not collinear. That means they need to form a triangle if connected. Okay, are points R, N, M, and X coplanar? So are they all on the same plane? So let's see. I'm going to erase some stuff so I can see what's going on a little better. And I'm going to go ahead and dot all those points. So there's R, there's N, there's M, and here's X. So N, M, and X are on the same plane. They're all on plane V. R is above plane V because remember that line RN pierces plane V at point N. So that doesn't work out for us. Those four are not on the same plane. Okay. Now R, N, and M are on the same plane, but then X is not. So this is going to be no. Name two rays shown in the figure. So pick an endpoint and go in either direction. So I'll go with NR. Start at N and go to R. And I could also go with CM. There are a whole bunch more. Okay, so you could have different answers for these. Just make sure you have an endpoint, and then when we go out the other direction, there's an arrow in that way. Name a pair of opposite rays with endpoint N. So lots of answers for this one also. We could go with NA, and then the other side of that would be NX. So you may have different answers than mine, but they could still be correct as long as they have the same endpoint and they're pointing in opposite directions. So for instance, NA and NM would not work even though they share the same endpoint. They form an angle when they attach. So how many lines are shown in this drawing? Let's go back and look again. I see 1, 2, 3. One here, one here, and then the one that pierces the plane or intersects the plane at N. So the green one, the blue one, the red one. So this is 3. All right, let's flip the page and see what's on page 2 here. On page 2 here, for exercises 1 through 6, determine whether each statement is always, sometimes, or never true. Okay. So GH and HG are the same ray. So GH and HG. Well, in GH, the endpoint is G, and in HG, the endpoint is H. So these are never true. These are going to be opposite, okay? So GH would be this one, and HG would be that one. So they're never going to be the same. All right, Ji and Jl are opposite rays, so this could be true. We could draw it like this. Here's Jl, and then here's Ji. They are opposite rays. Or we could draw it so that I is down here somewhere. And now they're not opposite rays. So this is sometimes true. It depends on how we draw it. Okay. A plane contains only 3 points. This is never true. Okay. A plane can be named with 3 points, but a plane contains infinite number of points. That's what makes it a plane. 3 non-collinear points are contained in only one plane. This is always true. Okay, that's how we name a plane. We pick 3 non-collinear points, and there's only one plane that can go through it. Okay. If EG, line EG lies in plane X, and G lies in plane, then point G lies in plane X. Okay, so EG is in the plane. Okay, then is G in the plane? And this is going to always be true. You can't draw the line that contains a point in the plane and then not have the point be in the plane too. Okay, if 3 points are coplanar, that means 3 of them fall in the same plane, they are also collinear. Okay, this is going to be sometimes true. I'll draw both ones. So here's my plane, and we could put 3 in a row and say, okay, that they're in the plane. Okay, or and then they're collinear, and then we could also put 3 not in a row, do them in blue, and these are in the plane, but they're not collinear. You cannot draw a line that goes through all 3. Okay, so sometimes true. Is it possible for one ray to be shorter in length than another? Okay, this is going to be no. You would think it would be. You look at it with a ray and you cut it off a little bit. So let's say this. Here's a ray. Okay, this is AB. And here's another ray, CB. And you might say, well, look, AB is clearly longer than CB. But remember, they go on for infinite amount of time. Okay, so it doesn't matter. They're both infinite long. Okay. Open-ended question here. Draw a figure of 2 planes that intersect in ST. So we want ST to be the intersection. So this is kind of a hard figure actually to draw. So here's a trick. I'm going to start with this. And we'll go here, and here, and here. All right, so there's my 2 planes. This one's plane, let's call it P, and this one's plane Q. Okay, and then we're going to draw ST where they intersect, and the intersection is going to be a line. So there's my intersection, and I'll put S and T right here. There's S, and there's T. Okay. So it's kind of hard to draw to make it look good. So I usually start with 2 X's and then connect them and make sure I make some of it dotted on behind who's behind which one at which time. So this plane's kind of in the front over here on the left, but then on the back side, this part's in the back, so we didn't get dotted. And the same with the other one. So plane P starts on the front and the left, and plane G starts in the front on the right. All right. Postulate 1.5, remember postulates we don't prove. Okay, so it's a ruler postulate. Every point on a line can be paired with a real number. This makes a 1-to-1 correspondence between the points on the line and the real numbers. The real numbers that correspond to a point is called the coordinate of that point. And we've been working with number lines since, I don't know, 2nd, 3rd grade. So you can always divide up our line and decide where the middle is at 0 and then start counting out. And remember, between each point, there's infinite other points. If you say to me, well, what's some place between 1 and 2? Well, 1.5. What's some place between 1 and 1.5? Well, 1.3. And we can keep going. No matter what 2 points you tell me, I can always find one in between. And that's why there's an infinite number of points on any line. Okay? All right, so we're going to need this postulate to allow us to measure lengths of segments. So the distance between A and B is the absolute value of the distance of their coordinates at A and B. So let's say A was at 1 and B was at 4, then the distance is going to be the absolute value of the difference. So 1 minus 4, take their absolute value, is going to be the absolute value of -3, which is 3. Or say, well, we'll start with the 4 first. Then this is the absolute value of 3, which is 3. So that allows us not to have to worry about the bigger ones first or the smaller one first. We just take the absolute value first. So the value AB, notice there's no line segment on top of this, or the length of AB. They're the same thing. Okay, so the value of AB is a number, 3. The length of line segment AB is also a number, 3. Okay, all right, let's flip it over. Draw a number line and then plot S on the number line at -3 and plot T on the number line at 2. All right, so here's 0, 1, 2, 3, 4, 5, 1, 2, 3, 4, -5. We're supposed to put S at -3. So there's S, and we're supposed to put T at 2. What is ST? So ST is not a line segment, it's the length of that line segment. So if I count this out, 1, 2, 3, 4, 5. So this is easy, this is 5. But if we want to really show the work for this, we would do, well, get that 5 by doing the absolute value of -3 minus 2. Okay? Or 2 minus -3. Doesn't matter which one we put first. Okay, we have one more postulate here. This is postulate 1.5, the segment addition postulate. Okay. Now, when you're writing down your postulates, which I really suggest you start in a little notebook, maybe from the back of it or just somewhere in there, pick some pages and start writing them. You can memorize this one by the name segment addition postulate, or you can do the long thing here. So long thing says if 3 points A, B, and C are collinear, and B is in between A and C, then the AB plus BC is AC. So this one makes kind of sense. So here's 3 collinear points, A, B, and C, and B is in between them. And this short part here in green plus this other short part in red is equal to the distance of the long one. It just makes sense. The 2 short ones add up to the long one. Okay. And we're going to use this to help us solve some things. So for instance, in number 10, if EG is 59, so that means the whole distance is 59. What are EF and FG? So here we're going to write an algebraic equation. So we're going to say the 2 short ones are 8x minus 14 and 4x plus 1 should add up to the long one, which is 59. So 8x plus 4x is 12x, and -14 plus 1 is -13. And then we can move the 13 to the other side. So 12x is equal to, let's see, I think that's 72. And then if we divide both sides by 12, we get 6. All right, so this asks, how long is EF? EF, of course, is not 6 long. 6 is how long x is, how big x is. So to get the length of EF, we have to plug 6 into this equation. So 8 times 6 minus 14. 8 times 6 is 48, and 48 minus 14 is 34. So there's the value of EF. The value of FG, well, I'm going to plug into the formula, but we don't really have to do that. I'll show you why in a second. It's going to be 4 times 6 plus 1. 4 times 6 is 24. 24 plus 1 is 25. Notice that these two numbers add up to how much? Oh, 59. Okay, so I knew already if one of them was 34, the other small one should have been 34 subtracted from 59, which would be 25. Okay, all right, but I wanted to show it algebraically. When numerical expressions have the same value, we say that they are equal. Similarly, and 2 segments have the same value, we say that they are congruent. So we add a little squiggly on top. So we might say 5 is equal to 5, but we would say that AG is congruent to GA. Okay? All right, that's my example. Let's flip it over and check our last page here. The midpoint, we have a new definition here, of a segment is the point that divides the segment into 2 congruent segments. Okay, so here's a segment. The midpoint is going to split this into 2 equal parts. So that would be my midpoint. And to show that they're equal, we can put little marks on here. Okay. All right, a point, line, and array or other segment that intersects a segment is at the midpoint is called its bisecting segment. So this thing would bisect the segment. So a point, line, and ray or segment is called a segment bisector in this case. So let's illustrate one more time. All right, so here is a segment. We'll call him AB. And let's make a line intersect this, okay, and bisect it actually. So this could be line L. And here's going to be my midpoint. And to show that it's the midpoint, I'm going to put little marks on here to show that they're congruent. Okay? So in this case, line L bisects, not just intersects, but bisects. Bisects is like a special intersection where it splits it into two equal parts. Line segment AB at point M. So we could write it like this. Line L bisects line segment AB at point M. And point M is the midpoint, the halfway in between point. All right. I think we have one more question down here, number 11. Q is the midpoint of PR. What is PQ, QR, and PR? So what are the values of those three things? So Q is the midpoint of this. It doesn't look like a midpoint. It looks a little too far to the left, but it's supposed to be our midpoint. So it's drawn misleading on purpose. So let's see, that means since the midpoint, then PQ should be equal to QR. So PQ segment should be, or the value of PQ should be equal to the value of QR, because Q is the midpoint. All right, so then I replace them with their algebraic values, 6x minus 7 and 5x plus 1, and now we'll solve it. I'll move the 5x over to make x minus 7 equals 1. And then I'll move the 7 over to make x equals 8. So now I know the value of x. I can plug that in to find each one of these. So algebraically, PQ's value should be 6 times 8 minus 7. 6 times 8 is 48, and 48 minus 7 is 41. QR's value should be the same, but let's just double check it to make sure we did our math right earlier. 5 times 8 plus 1, 40 plus 1 is 41, so that's great. It's a midpoint, so these two should be equal. And then I know the big one, PR, is going to be equal to PQ plus QR, which is 41 and 41 for 82. Okay, we can take both of those algebraic things, plug in again, and add up the answers, or we can just know that that's that. So 41 plus 41 is 82. All right, that concludes the notes for the day. I'll see you in class next time.